In the next few segments, we'll look at Assembly's version 2, which adds inventory tracking and a major new design pattern, which is prototype. Now, in Assembly's V2, we'll take orders for components and fill the orders by drawing parts from an inventory of parts, determining the cost of an order by totaling the cost of all parts used. Most of the interesting code is in the inventory classes, but let's start with a quick look at order here, which represents a single order. Now, an order is always for just one copy of a component, and may be for either a part or an assembly. And as such, it may use anywhere from one to many parts, since even a single assembly may include many parts. Assembly's version 2 keeps track of how the inventory of parts is used, including which orders used which parts. So the order class will show up in the code for inventory tracking. As you can see, each order has an ID, and the name of the component to build, and then a reference to the component that was actually built for the order. Now, this reference is initially null, but will be set once the order is filled, and we'll see how that works later. For now, it's enough to understand the ID and component name fields. Now, Assembly's V2 tracks inventory for each part, as we said, with an initial inventory read from the inventory.txt file. Each line of this file gives information on an inventory lot. Think pallets or boxes of parts. Each inventory lot has an ID, the type of part, a per part cost, and a count of parts in the lot. And note, by the way, that the per part cost varies by inventory lot, even for the same kind of part. Bolts in this lot are 23 cents, and bolts in this lot are 25 cents. Now, Assembly's V2 uses the inventory lots in increasing order of costs, using up the cheapest inventory lots first, and it keeps track of which orders used parts from each inventory lot. So if there is some future problem with the parts in that lot, the affected orders can be found. Class inventory lot keeps track of all this information for one inventory lot. The member data here are largely self-explanatory, except perhaps for this sorted map. So let's talk a little about that and start with a question. Look up java.util.sortedMap and answer the question, how does it relate to the map interface? This is a new interface we're seeing here, what we do know the map interface. How do they relate to each other? And what capabilities does sorted map add in general terms? What does it require of its key type that map does not? And again, in general terms. And what recently discussed class implements sorted map? Look at the implementing subclasses, in other words. And then hopefully after a bit of investigation in the Java docs, the conclusion you might have come up with, here is the sorted map interface, is that sorted map is actually a sub-interface of map. So it extends map. And the documentation makes it fairly clear that it keeps the keys in order. And when you look down in the code here, the methods, it does add a few more methods, like for instance first key and last key, that will return the first and last key in sorted order. And these would work only if there is some way of sorting the keys, of ordering the keys. So it requires keys that can be compared to see which is less or greater. If we look at the implementing classes, we can see that it is implemented by treeMap, which is a class we already know, of course. And that makes sense, since a binary tree would keep its keys in sorted order, as opposed to, for instance, a hash table, which would not. So, sorted map requires a key type with some means of being compared. Elemental numerical types are compared by relational operators like less than or greater than, but a key has to be an object. So how do we express relational comparison of objects in an object-oriented design? Well, Java lets you do this in two ways. First, and most common, is for the class to implement the interface comparable. And it's a generified interface, comparable T, with the T being the class type that you're comparing. This interface has one method, compareTo, which relationally compares two objects of the class, and which the implementing class must override. There's our override of it for inventory lot, for instance. Now, before we get deeper into inventory lot, here's a question regarding string. String is an excellent example of a class that does this, implements comparable, and defines a compareTo method. Look up its Java docs, and you can see that it does those two things. How does compareTo determine which string is greater? And what value does it return? Check just the return type documentation. All the heavy specification above it is hard to plow through. So if I want to check string S1 and see if it's less than string S2, what would I write? So after a bit of investigation of the Java docs here, first do note that there's the comparable string, an interface implemented by string. And if we go down to compareTo, we get this information. Now, this may just be review, and that's fine if so, but you should understand that compareTo does a lexicographic, fancy looking term there, lexicographic dictionary order, in other words, comparison on the strings. And as the paragraph here indicates, it returns a negative value if the first string is less than the second one, a 0 if they're the same, and a positive value if the first is greater. So a check, for instance, of S1 being less than S2 would be written as something like if S1.compareTo S2 is less than 0. Or if you like instead, you can swap them and write it as if S2.compareTo S1 is greater than 0. Either one works. By the way, the negative if less, 0 if the same, positive if greater rule dates all the way back to the strcomp function in C from around 1970. It has spread to many different languages as a way to express all three possible relationships with a single integer return value. And if you need a mnemonic to remember it, it might help to imagine subtracting the two values. For instance, if I'm doing this comparison, then that is like saying S1 minus S2. If the first one were smaller in such a subtraction, then you'd expect a negative value, of course. And if they were the same, well, you'd get a 0. And if the first one were larger, you'd get a positive value. Okay, next question. Check the Java docs for comparable. It's in java.lang. And estimate how many classes implement it. See if you can identify about a half dozen that you already know. And returning from a bit of research there, here's the interface, and it's got a lot of implementing classes here. And it's almost a ludicrously long list. I'm not going to count it, but it's well over 100. Now in this list you might recognize, for instance, all the wrapper classes. There's integer, for instance, and character, and doubles in here somewhere. Yeah, it is right there. So all the elemental wrapper classes are in there. And, of course, string is in there right here. And quite a number of others. You might recognize some of them. It's obvious from that list that anytime someone wants their class to be comparable, they implement comparable and they override compareTo. And that's what I did, in fact, to inventory lot. We saw implements comparable at the top and a compareTo method down here at the bottom. Now, question 4. According to the very brief code in this compareTo, what makes one inventory lot less than another? Probably a pretty quick answer here. If the first one's cost is less than the other one's cost, then the subtraction of costs returns a negative value, and that would mark the first inventory lot as less the second. And of course, if the costs are equal, then a 0 is returned, and if the first cost is greater, a positive value is returned. So, there is often a close relationship between the compare to method and subtraction of some property of the objects being compared, which is why the compare to return value is specified the way it is. However, you don't have to use some subtraction. There are really no restrictions on what comparison rule you use. I compared inventory lots by cost to make it easier to sort by increasing cost in order to use the least expensive ones first. But I might instead have compared part names or used some more complex combination of properties. In fact, we will need to do just that, use a combination of properties to fix a serious problem with the compare to that we just wrote. We'll be adding inventory lots, to a tree set in a later segment. And the way it is now, two different inventory lots with the same cost will be regarded as equal, and the tree set will refuse to add the second one. So, question 5. Fix this by making the compare to method sort by ID number if the costs are the same, so that, for instance, if two inventory lots have the same cost, then the one with the lower ID will be considered less. And returning from some thought there, there are a number of different ways you could do it, but you'll need something like this. We'll return if the costs are not the same, then the same subtraction we already had, cost minus other cost. But if they are the same, then we'll return the difference of their IDs. And this is a typical pattern for two key comparisons. If the primary key values are unequal, then use the primary key compare result. Otherwise, fall back to the secondary key. Now, there is one style rule that a well-behaved compare to will follow. If equals returns true, then compare to should return 0, and vice versa. To use the official term, compare to should be consistent with equals. Some library classes, including many implementations of map and set, expect this, and they'll be baffled, for instance, if compare to returns a non-zero value but equals says the objects are equal. So, did we obey that convention here? Is the compare to of inventory equals consistent with equals? If so, why? And if not, fix the problem by adding needed code. And a hint here, you're going to need to figure out just what equals method is in force for inventory lot, since we clearly don't have one written yet. Okay, returning from some research, and I would expect you might have gone up and looked at the object base class. If you didn't, stop again and go look at that, because that's where you're going to need to find the equals method. The short answer is we broke the convention. Inventory lot has no equals, and thus it defaults to the object equals. And the object equals, recall from earlier lecture, does a shallow equality comparison, and thus would return false for two different inventory lot objects with the same cost and ID, while compare to would return 0 in that case, and indicate that they are equal. We need to add an equals implementation that does a deep comparison to fix that, like this one here. So now the two objects will be equal if their costs are equal and their IDs are equal, and equals will agree with compare to. In closing, I should mention that the ideas we've just discussed extend well beyond Java. Abstracting the ability to be compared as an interface or method is a common object-oriented design, and the importance of agreement between a deep equality function and a compare function is also a common theme. In the next segment, we'll look at the other way to specify relational comparison of objects in Java.